Okay, this is the first video about graphing trig functions with, in terms of handouts, it starts with handout 6.5. So I think the first ones we're going to start out with talking about are the graphs of sine and cosine. And to get an idea of this, let's just recall the definitions of sine is y over r, and cosine is x over r. So if we're talking about within a quadrant, meaning we're forming a triangle, well, y and x are legs of the triangle, and r would be the hypotenuse. So when we're within the quadrant, in other words, forming a triangle, the ratio of y over r and x over r, or I should say the absolute value of those ratios, will be less than 1 when we're within a quadrant. It could be negative, hence the absolute value, but the absolute value is going to be less than 1, which makes sense because the legs of a triangle are always less than the hypotenuse. So the extremes will be when we're on the axes. So if we look at a unit circle again, and remember in the unit circle, r by definition is 1. So I talked about this in an earlier video, but it's worth mentioning again that in the unit circle, since r is 1, and each of these points are, of course, x comma y, when r is 1 in the unit circle, let me do a different color, sine theta is simply equal then to y, and cosine of theta is simply equal to x. So when I write all these points, again, only in the unit circle, it can be thought of as cosine theta, the x-coordinate, comma sine theta. So going around the circle, all the x-coordinate is what the cosine would be at that particular angle, and the y-coordinates are what the sine would be at the particular angle. So this can help us draw the graphs. So let's look at this first. Let's look at the graph of sine of theta. Now, we already said that when we're within a quadrant, we're forming a triangle with the absolute value of the ratio then being less than 1. So it comes to stand that the biggest that sine can be is 1, and the smallest is negative 1, because you're never going to have the case where a leg is going to be greater than the hypotenuse. So let's plot these crucial points here, which are where it's changing sign as it's going around the circle. So if I were to plot, let's start, of course, by the way, this x-axis, the input, we're going to graph y equals sine of x instead of sine of theta. So we're graphing y equals sine of x. So the input, or the x-axis, is my angles, and the y-axis is my ratios. So sine of 0, if we look over here, is 0 at the y-coordinate. And then it reaches its high point at pi over 2, in which case it's going to be 1. And between 0 and pi over 2 radians, I'm going to have fractional values. Like, for example, pi over 6 would be 1/2. Pi over 3 would be root 3 over 2. Pi over 4 would be root 2 over 2. So I would be the output would be fractions less than 1. So it's going to take on a curved look. And then I've got pi, it's 0. I'm going to extend my x-axis here so it's longer. And then continuing around the circle, we've got 3 pi over 2 will be its lowest point, and that lowest point being negative 1. And then 2 pi back up to 0, and then continuing around the circle, if we were to keep going, I'd be up at pi over 2 again, or after 2 pi, this is 5 pi over 2, back up at 1, and then I would be at 3 pi, and so on. And it would just keep on going in the same fashion. And we could go negatively around the circle. If I'm at negative pi over 2, and so this means we're going clockwise here. Well, at negative pi over 2, The y coordinate is -1. At negative pi, I'll be back at 0. And then I should be careful here to make sure my interval is the same here. -3 pi over 2, that's back up here. So that would be where I'd be at my high point. And then -2 pi, I'm back coterminal to where 0 is. Oops, didn't mean to do the yellow. -2 pi, I'm at 0. And then it would just continue to go as we're going around the circle. Well, a function like this that repeats itself after a given interval of the domain is called periodic. So sine is a periodic function, and the period is how often, the interval of the domain, how often it goes before repeating itself. So the period in this case of this function would be 2 pi. Because notice it repeats itself. So if let's trace this here. If I start at 0, it continues along this path, taking on different values, and then it repeats itself when it gets to 2 pi, which makes sense as it goes around the circle, and then it will start all over again. It will start at 0 and go up. So when I'm looking for what the period of a function is, I tend to start at 0 and see, okay, at 0, it's starting at 0 and going up. How long before that happens again? And in this case, it was 2 pi before it happens again. So the period of the function is 2 pi. Another important piece is the fact that let's talk about what the domain and range are. The domain of this function is all reals. There's no restriction on what I can input into the sine function. And the range is -1 to 1. And you may have heard this term before in physics. The term oscillates. So this function is oscillating between -1 and 1, or repeating itself. Another thing that you'll hear me talk about is interval width. So in this case, the interval width is pi over 2. And sometimes I write that as IW, and that's the width between the various points, the crucial points that I plot. Another thing to point out here is the high point here is, or the peak, as sometimes you'll see me refer to. How often do peaks occur? Well, in this case, in the case of just sine of x, we'll see a peak starting at pi over 2. And how often do I get a peak? Well, I get another peak at 5 pi over 2. So we say that peaks occur every pi over 2 plus k pi, 2k pi, sorry, not k pi, not pi apart, 2k pi apart. Let me erase that. And again, so we say that there's a peak every pi over 2 plus 2k pi. And so in this case, when I'm visually looking at this, there's a peak at pi over 2. There's another one at 3 pi over 2. And if I keep adding integer multiples of 2 pi, I would get all the peaks. In terms of another language, we've got our low points, or our troughs, are occurring. In this case, I could say every 3 pi over 2 plus 2k pi, or I could choose a different angle to start from to talk about my my troughs. I could say every negative pi over 2 plus 2k pi. So that's important as well. And the final piece I want to highlight is the fact that, remember how we described functions in the past as even, odd, or neither? Well, visually, now that we have a graph, we can see that this function is symmetric across the origin. If I were to flip the side to the right of the y-axis over the y-axis and the x-axis, the graph would line up. And we call that type of function an odd function. So sine is an odd function. And another way to justify, and again, because it's origin symmetry, but another reason is if I do sine of negative theta, well, if it's odd, that should be equal to negative sine theta. And in this case, that in fact is true, because if I'm running out of room here, But if I were to just, let me scrunch it up a little bit. Let's take, if I were to look at, if this here is theta, if I were to look at negative theta, well, negative theta would be down here. And if I were to take the sine of negative theta, as we know from our previous work, in this fourth quadrant, the sign is negative, so it indeed would be equal to negative sine, the positive version of that angle. Okay, so that's the sine function. Up next, in the next video, I'm going to talk about cosine.